Section 3.2, Some Simple Patterns of Chemical Reactivity. In this section, we examine three types of reactions that we see frequently throughout this chapter: combination reactions, decomposition reactions, and combustion reactions. Our first reason for examining these reactions is to become better acquainted with chemical reactions and their balanced equations. Our second reason is to consider how we might predict the products of some of these reactions, knowing only the reactants. The key to predicting the products formed by a given combination of reactants is recognizing general patterns of chemical reactivity. Recognizing a pattern of reactivity for a class of substances gives you a broader understanding than merely memorizing a large number of unrelated reactions. Combination and decomposition reactions. In combination reactions, two or more substances react to form one product. For example, magnesium metal burns brilliantly in air to produce magnesium oxide. Magnesium solid, two atoms of magnesium solid plus one molecule of oxygen gas yields 2 molecules of magnesium oxide solid. This reaction is used to produce bright flame generated by flares and some fireworks. A combination reaction between a metal and a nonmetal, as in equation 3.6, produces an ionic solid. Recall that the formula of an ionic compound can be determined from the charges of its ions. When magnesium reacts with oxygen, the magnesium loses electrons and forms the magnesium ion 2+. The oxygen gains electrons and forms the oxide anion 2-. Thus, the reaction product is MgO. You should be able to recognize that when a reaction is a combination reaction and to predict the products when the reactants are a metal and a nonmetal. Table 3.1, Combination and Decomposition Reactions. Combination reactions. A plus B yields C. Two or more reactants combine to form a single product. Examples: carbon plus oxygen gas yields carbon dioxide gas. Nitrogen plus three hydrogen molecules is 2 molecules of ammonia. Calcium oxide plus water yields calcium hydroxide. Decomposition reactions are the opposite. A single reactant breaks apart to form two or more substances. Many compounds react this way when heated. C yields A plus B. Examples: two molecules of potassium chlorate break down into 2 molecules of potassium chloride plus 3 oxygens. Lead carbonate breaks apart into lead oxide plus carbon dioxide gas. Copper hydroxide decomposes to form copper oxide plus water. Figure 3.6, Combustion of magnesium metal in air, a combination reaction. Combination between magnesium and oxygen to form magnesium oxide. The reactants are magnesium metal, oxygen, 2 magnesium metal atoms, 1 molecule of oxygen to produce 2 molecules of magnesium oxide. In a decomposition reaction, one substance undergoes reaction to produce 2 or more substances. For example, many metal carbonates decompose to form metal oxides and carbon dioxide when heated. Calcium carbonate, in the presence of heat, yields calcium oxide plus carbon dioxide gas. Decomposition of calcium carbonate is an important commercial process. Limestone or seashells, which are both primarily calcium carbonate, are heated to prepare calcium oxide, known as lime or quicklime. About 2 times 10 to the 10 kilograms or 20 million tons of calcium oxide is used in the United States each year, principally in making glass, in obtaining iron from ores, and making mortar to bind bricks. The decomposition of sodium azide rapidly releases this reaction to inflate safety airbags in automobiles. 2-sodium azide breaks apart into sodium metal and nitrogen gas. The system is designed so that impact ignites a detonator cat, which in turn causes sodium azide to decompose explosively. A small quantity of a small quantity of sodium azide, about 100 grams, forms a large quantity of gas, about 50 liters. Combustion reactions. Combustion reactions are rapid reactions that produce flame. Most combustion reactions we observe involves oxygen from the air as a reactant. Equation 3.5 illustrates a general class of reactions involving the burning or combustion of hydrocarbons. Hydrocarbons are compounds that contain only carbon and oxygen, such as methane or ethane. Hydrocarbons combusted in air to react with oxygen to form carbon dioxide and water. The number of molecules of oxygen required and the number of molecules of carbon dioxide and water formed depend on the composition of the hydrocarbon, which acts as the fuel in the reaction. For example, the combustion of propane, a gas for cooking and home heating, is described in this equation. Propane plus 5 oxygen molecules yields 2 carbon dioxide molecules and 4 water molecules. Figure 3.8. Propane burning in air. Liquid propane in the tank, C38H8, vaporizes and mixes with air as it escapes through the nozzle. The combustion reaction of C388 and oxygen produces a blue flame. The state of the water in the reaction, H2O gas or H2OL liquid, depends on the reaction conditions. Water vapor, H2O gas, is formed at high temperatures in an open container. Combustion of oxygen-containing derivatives of hydrocarbons, such as alcohol, also produces carbon dioxide and water. The rule that hydrocarbons and their oxygen-containing derivatives form carbon dioxide and water when they burn in air summarizes the behavior of about 3 million compounds. Many substances that our body uses as energy sources, such as sugar glucose, react with oxygen to form carbon dioxide and water in our bodies. However, the reactions takes place in a series of intermediate steps that occur at body temperature. These reactions that involve intermediate steps are described as oxidation reactions instead of combustion reactions.